Hi, in this video, we'll discuss on Kepler's law of planetary motion. In the early 17th century, the German mathematician and astronomer Johannes Kepler formulated three famous laws for planetary motion, which are known as Kepler's law. He came to these three laws by analyzing the data observed by Tycho Brahe, who was the renowned astronomer and alchemist during his time, and Johannes Kepler was his assistant. And later on, Newton showed that these three laws can be derived from his law of gravitation. Anyway, in this video, we'll discuss on Kepler's law. In his first law, he talked about the shape of the trajectory of the planets which are revolving around the sun. He said that all planets move around the sun in elliptical orbits, okay, where the sun is situated at one of the two focal points. So the shape of the trajectory is elliptical in nature. Okay. And we know an ellipse has two focal points. Sun is situated at one of them. Okay. We also know that an ellipse has eccentricity between 0 and 1. The eccentricity E is less than 1 and greater than 0. More eccentricity means more squeezed. Let's say this ellipse has eccentricity E1. Okay, and this ellipse has eccentricity E2 and this ellipse has eccentricity E3. We can see that this ellipse is more squeezed than this one, so E1 is greater than E2, and this ellipse is more squeezed than this one, so E2 greater than E3. We will talk in more detail about ellipse when we will do some examples. Let's take an example. We all know about the comet Halley, which is visible once in 76 years. Okay. If the eccentricity E of its orbit is 0.97 and the perihelion distance RP is 8.9 into 10 to the power 11 meter, then find the aphelion distance, which is the farthest distance from the sun. Okay. Let's draw a diagram. From the first law, we know that the orbit is elliptical in nature and it has two focal points F and F prime. Here, sun is situated at one of the two focal point. Okay, here sun is situated at F, and this is the major axis. Okay, the length of major axis is twice A, and this is the minor axis whose length is twice B, and the length between S and the center O, that is A times E, where E is the eccentricity. In this problem, the eccentricity is given, that is 0.97, and the perihelion distance is given, that is the shortest distance from the sun, that is SP. SP is given, and we have to find out the farthest distance from the sun, that is from S to A. Okay, we have to find out this distance. So the perihelion distance RP equal to SP, right? So this is equal to OP minus OS, right? OP minus OS. OP is the length of the semi-major axis, that is A, minus OS, that is A times E. Okay. So this is equal to A into 1 minus E. Now if we put the value of RP, that is 8.9 into 10 to the power 11, and the value of E, that is 0.97, then we will have A equal to 2.96 into 10 to the power 13 meter. Okay. Now aphelion distance, that is SA, equal to SO plus OA. Okay. SO equal to A times E plus OA, that is the length of the semi-major axis, that is A. Okay. That is equal to A into E plus 1. Okay. So if we put the value of A, that is 2.96 into 10 to the power 13 meter, and E, that is 0.97, then we will have 5.83 into 10 to the power 13 meter. One more thing is that if we know the eccentricity E and the length of the semi-major axis, then we can also know the length of the semi-minor axis B. From this relation, E equal to square root of 1 minus B square by A square. Okay.